I highly recommend that you watch Mechanics Part 1 before you can go through Mechanics Part 2, because the material covered in this section requires the background that we have done in Part 1. Part 1 covered an overview of vertical projectile motion together with calculations. In this section of mechanics, we are going to look at vertical projectile motion graphs. There are basically three graphs that we are going to study: the position versus time graph, the velocity versus time graph, and the acceleration versus time graph. We are going to focus our attention on each graph so that we fully understand it. We'll begin by looking at lesson 2, where we study position versus time graphs. The position versus time graph is drawn using the equation of motion. Change in y is equals to initial velocity times change in time plus 1/2 times the acceleration due to gravity, because remember this is projectile, multiplied by the square of time. We know that when we have delta y, which we call the displacement, it can be expanded so that it is written as the final position minus the initial position. Basically, that's how we define displacement, to say it is the difference between the final position and initial position. And this would be equal to vi change in t plus 1/2 the acceleration time squared. The equation can therefore now be written in a way that I have the final velocity is equals to. I'm going to also rearrange this side so that I start with the half g change in t. So I'm going to have here 1/2 g time squared plus, here I'm going to say the initial velocity times time, and of course our initial position would be a positive yi. If we inspect this equation thoroughly, we can see that it is actually in the standard form of a quadratic equation. What I mean is that we actually now have f of x is equals to ax squared plus bx plus c. Now, the yf, which is the final position of our projectile or the object, is the same as the f of x. The 1/2g is the same as a. The vi here is the same as b. The yi is the same as c. This equation here behaves exactly the same way as the standard form of a quadratic equation. And this is the reason why when we draw position versus time graphs, they are always a parabola, because they are of this form. And that automatically translates to the fact that this equation that we have here of motion actually has the following properties, or the same properties as a parabola or a quadratic function, if you would like to put it that way. Now, when we break it down, you would see that the 1/2g Remember, it is the same as A. It behaves in the same way as A, this whole guy here. It will determine the shape of our parabola. It will tell us the shape of the parabola. For instance, if our half G is greater than 0, meaning it is positive, if it comes out to be positive, to say it is greater than 0 means it is positive, then our curve or our parabola should be concave up. This means that our parabola should be a parabola that looks like this. Now, what does this mean in terms of looking at the physics? It means that our direction in this case would actually be downwards. Positive will be downwards, because we're saying here that this here is positive. It means downwards will be positive. The reason being is because the acceleration due to gravity always points downwards and is given by G, and we know that it is 9.8 meters per second squared. It is always downwards. So now, if we say this number here, the G is positive, because remember the half is already positive. So if we say the G is positive, that means the whole thing will be positive. And our graph then becomes concave up. It becomes a happy graph. What we used to say a happy graph in mathematics, it then becomes a happy graph. So that means downwards is positive, because the acceleration due to gravity is actually going downwards. So that means our direction is positive there. The converse is true. If 1 over 2 is actually less than 0, in other words, if it is negative, that means the direction implies that downwards should be negative, because again here we know that G is always pointing downwards. But if I'm saying I'm having a negative G, which is negative 9.8 meters per second squared, when I put the negative 9.8 and multiply with a half, I'm going to get this whole thing to be a negative. Now that means that this downward direction is now the negative direction. It means we have chosen down as the negative direction. And of course, we know that if our A here is a negative, the 1 over 2G is a negative, we must have a set graph. And we said this is a set phase. You know, in mathematics, how we teach these graphs, we say negative would mean sadness. It gives you negative vibes. And positive would mean happiness. It gives you positive vibes. These are familiar phases, the positive and the negative phase. The other thing that we have to note is that the Y initial here means the initial position of the projectile or our object that we're dealing with. In other words, it tells us the position at which we start to throw our ball. Now, when we look at the equation of a parabola, we see that this part of the equation, C, is actually the y-intercept. That's where our graph will intercept the y-axis. And we know that this happens when the x is 0. Because if you put 0 here, that's where we get the coordinates of 0 and C. We get the y-intercept. Now, if you look at these equations properly, you would see that the x is actually the same here as the t. That means in this case, our y-intercept in terms of this equation will occur when the change in t is actually 0. That is at the beginning of our motion, when the object is being thrown. So this means already our y-intercept should always be when the object is thrown, at the time when the object is being projected. And as we have said just now, the t would be the independent variable because it has the same properties as x when we compare these two equations. So it is the independent variable and it sits on the x-axis. So this means that if I draw my Cartesian plane, we are going to have the x-axis represented by time, and it will be measured in seconds. It is the horizontal axis, it is the independent variable. And the yf here, the y final, remember we said it is the same as the f of x. In other words, remember f of x is a function of x. In other ways, it depends on the value of x. As we change the values of x, the independent variable, the value of f of x also changes. The same is true with y. It depends on the time. The time is the independent variable. So this means as the time changes, the position of the object will also change. It will occupy different positions. That's why normally we just represent the y final using the symbol y, because it occupies different positions. Now this y, in other words, what I'm saying here is that this y final is actually a function of time because it depends on time. It is the function of time. The position therefore must be a dependent variable and it should be drawn on the y-axis. In this Cartesian plane, it means it is going to sit like this. So this is where you're going to get your position measured in meters. Remember, position is measured in meters. It's similar to finding a height, except that position is a vector quantity. Height will be a scalar quantity. Now, what I'm saying here is that all the time, when you draw a position versus time graph, your independent variable will be time, your dependent variable would be the y there. It will change as the time changes. And we expect here to have a parabola, a happy face, a sad face, or a happy face, depending on whether our direction is down or upward. Meaning if our direction is positive or negative. Now let us look at a couple of examples where we draw these graphs using this method. We are going to look at the same three classic problems that we did in the first part of vertical projectile motion, where we looked at an object that is being thrown vertically upwards, dropped vertically downwards, and thrown vertically downwards with some initial velocity. We are going to sketch those three graphs. From those three graphs, you are able to draw other graphs that involves the ball where it bounces, or maybe someone is throwing the ball while they are in a hot air balloon, and etc. You should be able to draw any graph by understanding these three basic ones. We are going to do them in a form of problems where we provide methods or ways, step-by-step ways of how to sketch these graphs. Now this one would be question 1, which says to us that a ball is thrown vertically upwards from the edge of the balcony, and after reaching the maximum height, it returns to the reference point. Ignore the effects of air friction. Now we are saying here that a ball is thrown here with some initial velocity, Vi. So this ball will then go upwards because it's been thrown upwards and it's moving from the balcony. Then it reaches the maximum height, wherein it returns back to where it started. Now they call this where it started the reference point. The reference point means the origin. In other words, it means where our position is 0 meters. where we start to measure our position or our height. This is the reason why here we say our YO to mean the reference point is equals to 0 meters. And we then say this is the same as YI. That is to say that this is the initial position of the ball. This is where the ball starts. So we're saying the reference point YO is the same as the initial position because that's where the ball started. And they are at the 0 position because the reference point means 0 meters. Now, because they said we should ignore air friction, this means that we have a free-falling object, an object that moves under the influence of the gravitational force only. A typical situation of vertical projectile motion. Question 1.1 requires us to draw a position versus time graph of the ball. And it further says that take down as negative. Now, to make sense out of this, I'm going to first write my direction here to say we have the direction sitting like this. I'm saying here that vectors that go in the upward direction will be positive and vectors that go in the downward direction will be negative because we're taking down as negative. If I focus my attention on the y-axis, because our projectile moves up and down, it moves in the vertical direction, and ignore this, I am able to actually draw an enlarged frame of reference just like I did there, where I'm going to say this is the positive direction and this is the negative direction because we're saying down is negative. So I'm extending this part of the reference frame. Remember, I'm using here the reference frame to choose my direction. Now, when I do that, I can see that positions that are from here, they will be measured at 0 meters because this is the reference frame. That's where our reference frame Y0 is equals to 0. This implies that any position above this point, any position that goes to this direction above this point, that the ball occupies as it goes up and coming down will be positive, and any position below this point would be negative because it will be going in the negative direction. I am only focusing on position here. Now, the ball will begin, it will have an initial position Y initial at the reference frame, meaning at 0 meters because it starts exactly at the balcony and the balcony is the reference frame. The ball will then occupy a higher position. It will go to the next position somewhere here, or height if you like. Now, to measure this position, we'll measure it from the reference point from 0 coming to that height there. We will say it moved, that it will be a vector that moves from 0. It's a vector that moves from 0 to that height. That's where the ball is now located in space, because remember, position is just the location of an object in space. Because the ball is moving upwards, it will then go to a much higher position or height. And this would mean we'll draw this as a vector that is measured from the origin, the reference point, the zero position, and going to that height. It is now in that height. So our position is now here. Eventually, the ball will then reach this position here, which is measured from the reference point again, and then it gets to that height. If you look at this height, is the largest height that we'll ever get, or the largest position that we'll ever get, because from here the ball will stop for an instant and then change direction to go downwards. I am going to label the first position that it occupied as positive y1 because it goes in the positive direction. It's a position, it's a vector that is pointing in our positive direction. And I'm going to label the second position that it occupied here as y2. It's going to be plus y2. It's a positive because it goes in the upward direction. And here we are going to label this as y max. And this is positive, y max positive, because it also goes upwards. Now, after the projectile stops for an instant here, it then goes downwards. And as it goes downwards, we know that it will occupy the same positions that it occupied when it went up. Because remember, we are studying vertical projectile motion. We are actually studying a projectile that goes up and comes down in a straight line. The trajectory is a straight line up and down. This path here that we've drawn here, it is not the true path or trajectory of the projectile. We're just drawing this path so that we are able to explain or maybe display the projectile on paper. Now, when the projectile goes down, it will occupy the same position that it did when it went up, which will be this position. And when you look at this position, it's really actually the same position that we occupied, the same height that we occupied of y2. So it will go back to y2. It will continue dropping down and come back here at the position here, which is the same height as y1. And eventually it will then come to the reference point, as they've said, which is the balcony, where it started at the 0 position. Now, there is a couple of things that we need to look at here as far as now using our equation so that we can plot the position versus time graph. We have here an equation that says y final is equals to 1 over 2g change in t squared plus v initial change in t plus y initial. In this equation, we said downwards is negative. That means our acceleration due to gravity. Remember, it is a vector that always goes downwards. It means here is a negative 9.8 meters per second squared because it goes in the negative direction. Now, if we put this vector here, we're going to have negative 9.8 times change in t squared plus v initial change in t. And here we said our initial position is 0 because the ball starts at the reference point. The ball starts moving at the reference point. So now here we're going to have 0. Now this would mean that our equation will then be simplified to be negative 4.9 change in t squared plus v initial change in t plus a 0. Now let us check something. The first thing that I'm going to look at is here the value of a here. To say my a is a negative, that means I expect a sad graph. The shape of my parabola should be a sad graph. And the other thing that I notice here is that my y initial is a 0, right, which is the y-intercept. In other words, my y initial, which is the y-intercept, is equals to 0. This means that my graph should intercept the y-axis at 0. And this is the initial position. In other words, that's where my graph will start, meaning this part here should be 0 when I draw it on the Cartesian plane, because the graph will start drawing it from this side going like that. Now if I put this information together, I'm going to have perhaps the first thing that we need to do is to write the title first of our graph, to say y versus t graph, position versus time graph. Our position is measured in the y versus time graph. Then now I'm going to put this in a sketch. Let's draw a straight line there. Let's try to draw a nice Cartesian plane. Now I'm going to have here, we said this will always be the dependent variable and this will be the independent variable. So always here I'm going to have my position measured in meters, then I'm going to have the time measured in seconds. Here we're going to have 0. It is the origin. That means that's where the time is 0 and also that's where our position is 0. In other words, it represents the reference frame and also represents where our clock reading is 0, where we start our motion. And we are saying here that the graph should be a happy face and it should start at 0. That means my graph will start here at 0 and give me not a happy face but a sad face and give me a sad face. Now when we draw this graph, it will be a graph that looks like this. The graph that starts at 0 and then it gives me a sad face because my A here through the 9.8 is a negative. Now that's simply how you'll basically draw this graph. It's a parabola based on those properties. When we want to interpret this graph to make sense out of it, we notice a couple of things here. It should match the motion that we described here. Now, when the time is 0, the position is also 0. We get a point 0, 0 here. And that makes sense because this is when the time is 0, where we start throwing the projectile. Our initial position is also 0. But obviously, after throwing the projectile, the time will increase. And we want to see that as it increases, what happens to our position. Well, we expect the position to also increase and decrease again. Now, what will happen here is that the time will increase to this point, and we see that the position has also increased. We get positive y1. As the time continues to increase to this point, the position further increases as well, and we get positive y2, which is this part here. And eventually we reach a point here. Maybe let me move it a bit so that it is somewhere in the middle. We reach a point somewhere here when the time continues to increase. And this time here, so here I'm having T1, T2. This time here I'm going to call it T max to say it is the time at the maximum height, because I can see that here I'm going to get the maximum height. I'm going to get Y max, which is this height here. Because I can see that after this height, after this time, when we go to the next time, the height that we get is actually below. So that means this is the maximum height. There is no any other height above this one. We don't have a graph here. Now, if we continue increasing our time further, we then come to the point where we go back to the height that we passed when we were going up. So this will be y2. This is this point here, y2. If we continue increasing our time again, we go back to this height here as well, which is y1, the height that we reached there as y1. So our projectile basically goes up as the time increases, reaches the maximum height, and goes down. Now this is very important because it means now that from here to this part here is actually the motion where the projectile goes up. And from here going down there, it means our projectile is really actually going down. This part of the graph represents when the projectile is going up, and this part of the graph represents when the projectile is going down. You will notice that I didn't draw anything this side because we are actually going to have negative numbers here, and we can't have time to be negative. It is possible to have negative positions. It's just that in this specific situation, when a projectile is thrown vertically upwards, it does not move. If we chose our direction to be negative, it moves actually above the positive side. It is actually located in, because it's going in the positive direction, it's located in that positive direction. The next part of the question says to us, draw a position versus time graph for the ball. But they say here now that take down as positive. What we do in this scenario is that we actually, let me erase so that I go through this again using the different direction that we've given. It's the same situation, but we change only the direction. So we change this direction here. Now what happens in this scenario is that we actually still have our reference frame, but in this case it will sit such that when we have a vector that goes up, that vector will actually be negative. Remember, we're saying here that down is positive. In other words, if this is positive, up should be negative. I then do the same thing. I take this part of the reference frame, enlarge it, and put it on my diagram here, so that this part here would be where we start measuring our position, because they said the balcony is the reference point, meaning that's where we have 0 position. Our reference point is equals to 0, and that's where we start throwing our ball. So all these three are the same. The height at which we throw the ball, or the position at which we throw the ball, is 0, and this position is the reference frame. Now from this we have said that the ball will then start at that 0 position. It will then occupy some position here. Then when we look at the position that it has occupied, it will be a vector that moves from 0 and goes to where the object is. But in this case, it's going to be a negative y1, because now I haven't changed direction now here. Because now we have our upwards being negative. Remember, we said going up now is negative, and we have our downwards being positive because we're taking down to be positive. That's why this vector is then now written as a negative. If we look at this again, you will see that the ball will then go to the next position somewhere here because it's going up. The vector will be measured from 0 position going to where the object is now located, giving us the height that it has occupied now. And then this height will also be negative y2. Again, it is a negative vector because this side of going up is chosen as negative. Eventually, then the ball will reach the maximum height, which will measure again from 0 and going to that maximum height. So this will be y max. And this y max will also be negative because it is pointing in the negative direction, which is upwards in this case now. As we know, the ball will then come to this position and come to that position. It will occupy the same positions that it had when it went up, because projectile motion is symmetrical. Now, this will also be measured as the same positions that it occupied here, negative y2, and then it will be lowered again to negative y1, and eventually it will then come to the reference point, which is the balcony where it started, where the initial position is 0, and it is the reference frame, which is the origin, is 0 as well. You have to note that in this case, the acceleration due to gravity will still exist, and it will be a vector that goes down, because remember, this vector is influenced by the force of gravity. It always points in the direction of the force of gravity, which is directly downwards towards the center of Earth. But now, in this case, we're saying down is positive. In other words, this vector that points downwards is pointing in the positive direction. It's pointing in this direction of our reference frame. If we look at this in terms of our graphs, if we take all this information that we have looked at now and try to draw a graph using this information, we can see that on our equation we have y final is equals to 1 over 2 times 9.8 here, change in t squared, plus v initial, change in t, plus 0. Remember, this last part here stands for y initial, and we're saying our y initial is 0 because the ball started at the reference frame. Now this will mean that we now have a positive value of a here. Remember, this part determines the shape of the graph, and if this is positive, it means happiness. We have a happy face graph. We expect our graph to sit like this, and our yi here we just said is 0, meaning where the graph should intercept the y-axis will be at 0 at the origin, and this is where the graph starts because it's the initial, so it's this point here. Now if I put all this information on my position versus time graph, I will have a Cartesian plane that is sitting like this, where I'm having y measured in meters, because we said y, the position, would be the dependent variable, and this side here we're going to have the time measured in seconds. Then we are saying that we have to have a happy graph that starts at 0 because our y-intercept is 0. You see here, this is the y-intercept. It cannot be a graph that starts here and be like that, because then now here we don't intercept 0, here we intercept some number that is there. That's why our graph is actually forced to start here at 0 and try to draw it such that it is symmetrical. Right, that looks much better. So now again, if we look at this graph, we can see that here that's where our time is 0 and our position is 0. In other words, on the vertical axis this represents the reference frame, but on the horizontal axis this represents where the time is 0, where we start throwing the ball. Now the ball will be thrown from here and then it will increase its height. So if I could get that different pen just to make sure that we understand this. So here is where the time is 0 and the position is 0. That's where we throw the ball. It is this point here where we have 0 time and 0 position, the reference frame. Now the time will increase as the ball goes upwards. That means we get to some point here where we have t1, and at t1 we can see that the position has increased. We're going to have y1. It has increased from 0 to this position, but it is in the negative direction, and that's exactly the direction that we chose because we said up is now negative. The ball will then continue moving as the time increases to the next position, which is the time t2, and this position will then be a position somewhere here, which is going to be y2. But again, it is in the negative direction of the Cartesian plane here on our axis of on the y-axis. This will be a negative as well, and that's the height that we discussed, that it will increase that height in the negative direction, because up in this case has been chosen as negative. At some point, as the time increases, we will reach a point where we have the maximum height here. In other words, this will be negative y max, because it is also in the negative direction. Then that means this time here I'm going to call it T max instead of calling it T3, because it is the time at the maximum height. It is the time the ball reaches the maximum height, because there is no any other height beyond this point. The graph does not exist above this point. Now when the time continues going further, you can see that we will get to a point where we reach the same height that we reached when we were going up. It is this point here, because after maximum height we have to go down. But again, it is also negative because we chose up as negative. And eventually we then going to hit the height here, which is this here, y1, where we started. And then the ball will eventually come back where it started, at the reference frame, where the height is actually 0. It is at the top of the balcony. In the same way, we can see that this part of the graph represents when the object goes up. It represents when the object was actually going up here, and this part represents when the object was going down. It is this part of the graph. Now when you look at the two graphs, they have the same shape really. They're both parabola, because we sketch them from the parabola here, the quadratic function. The only difference is that they are reflections of each other. This one is above the x-axis and this one is below the x-axis. So it's a function that has been reflected about the x-axis. And what makes these functions to be reflected is the value of our direction when our acceleration is positive and negative. Another important piece of information that we have to connect to these graphs is the time symmetry. How do I mean? If we look at, say, the graph that we have drawn, the first graph that we have drawn here, we have said that the time it takes from the point where it is projected vertically upwards to the maximum height here, this time is T max, is the maximum, is the time at the maximum height. That means here that from here to this point, we actually have change in T max, if I were to write it in terms of change in T. And we know from our previous lesson 1, when we introduced projectile, that the time that it will then take for the projectile to go downwards, which is here from here to coming back to the reference point at the balcony, will also be defined in the same way. It will be the same time it takes for it to go up. In other words, I'm saying this T max is also the same this side here. We also have T, changing T max. Now, to then get the total time, because here we are going to have T total. To define this total time in terms of an equation is going to be 2 times change in T max. If we take the time it takes to get to the maximum height and we multiply by 2, or perhaps you add the 2 times change in T max plus change in T max, it will give you 2 change in T max, and that will be the total time that it takes for the projectile to be in motion, meaning to go up and come down. This observation is true even in our second graph, because the time it takes to reach the maximum height here, change in T max, will be the same even here. We're going to have change in T max, and therefore because they are the same, the change in time total will also be defined in the same way for this graph to be twice change in T max. This relationship, you always have to look for it when you're dealing with projectiles that go up and come down. Now, in our diagram, it simply means that the time that it takes for the projectile to move from the balcony, which is the reference point, to go up to the maximum height here will be the same time that it will take to come down back to the reference point. And that's the time we defined to say it is going to be given by T total is equals to twice the time it takes to reach the maximum point. We are now going to look at another scenario where we draw the position versus time graph. By looking at question 2. Question 2 says a ball is thrown vertically upwards from the edge of the balcony and then falls back down. Eventually it strikes the ground. Take the balcony as the reference point and ignore the effects of air friction. So again, it means this ball is moving under free fall because there's no air effects. Now here again we are saying that we're taking the balcony as the reference point, meaning that's why we're going to measure our position to be 0. That's why we start measuring our position to be 0. That's why we're saying y0, which is the reference frame, is equals to 0. But also this is the initial position of the ball. So all these are equal to 3. They are equal, all these 3 are equal to 0. Now the first question 2.1 says draw the position versus time graph for the ball. And here we then say take down as negative. Again, that would mean if we choose our direction, vectors that go up will be positive because we're choosing down to actually be negative. And of course here we have the x-axis. We're not going to use it because our motion doesn't happen in the x-axis. Now what we have to then look at here is that our acceleration due to gravity g is going to be a negative 9.8 meters per second squared, because we chose down as negative and it is going in that negative direction. That would mean that our projectile will start at 0 position and goes to the next position here, which will be positive y1, and go to the next position here, which will be positive y2, because it's going in the positive direction. And then it will reach the maximum height here, y max. Then it will return back to this position and return back to this position until it comes back here at the reference frame. But in this case, it passes the reference frame and continue to going down. But now check here, when it goes down here, it then now has a position that is pointing in that direction. In other words, we're going to have position that is negative here, and as it goes down, we're going to have another position that is negative here until it gets to this position, which will also be a negative. So from here, we still have the same motion that we did in the previous example, except past this point, we occupy negative positions until we get to this position. So this means our graph, when we look at it, is going to be a sad graph again, because our 9.8 is negative, and it will start at 0 because our initial yi is actually 0. And so this would mean when I draw this, I'll say equation 2 here. I'm going to have my position versus time graph, and I'm going to draw my set of axes here so that I have time in seconds, then I have my position in meters. This is 0. Now we are saying here that the y initial, our position is 0 meters. So that means our object will start here at y, and it is a set graph. So it has to be a set graph like this. Now this graph will move from here at 0 where we start and goes like that until it comes back, but it will continue past the reference point, because when it gets to the reference point here, it then goes in the negative direction, as I have explained here, that when the projectile gets to this point, it then occupies negative positions here until it gets to the ground. So this will be the negative positions that it occupies. So what we're saying here is that when the time is 0, the position is also 0. When the time increases to t1, we have a position here, y1, which is positive. When the time goes to t2, we have a position here which becomes y2. Then here we reach the maximum height, y max. Then past this point, we occupy the same positions we occupied when we were going up, and then we get to 0 again at some point here when we're at the balcony. But after the balcony, when the time increases, we then reach new positions that are negative here, new positions that are negative until we get to the ground, which is negative positions there. So is still the same parabola that we had, but it moves a little bit downwards like that. And again, in this motion, from this part to this part, this will be upwards, and from this part going up until the ground will be downwards. That's how you will simply draw your position versus time graph under this situation. This question continues further to 2.2 to say draw the same graph, but here they change direction as we did in the previous one. I'm not going to do this one. I'll leave it up to you to try it using this method and see if you are able to come with the correct sketch. But do not worry. This study guide that I'm using is attached in the description of this video. Click the link and go download this study guide. It has the answers that you should get when you try to do it on your own. If you still struggle following this study guide to get the correct answer, leave a comment in the comment section for me to do a video explaining how to draw it. I'm going to jump to question 3, which says a ball is thrown vertically upwards from the edge of the balcony, and after reaching the maximum height, it returns to the balcony. In this case, they say take the ground as the reference point. So if you check this problem, it is still the same problem that we did in question 1, except in this case, we say now the reference point is actually here on the ground. We then also say ignore the effects of air friction. Now question 3.1 says draw the position versus time graph for the ball. Take down as negative. Again, it means here we are choosing upwards as positive because we say here down will be negative. Right, we're saying down will be negative. So that means if I take my reference frame here and extend it so that it is now enlarged and drawn on the sketch, I'm going to have this direction to be negative because we're taking down as negative. So it means vectors that go in that direction, specifically positions that go downwards, are negative, and the positions that are going upwards will be positive. Now, this would mean that our projectile will really start here in this position. And when you look at this position, it is now not going to be a zero, this position. The zero is actually at this point here. This is to say this is where we start to measure our position. Our origin is now here at 0. And you can clearly see that the y0, which is the reference frame, is 0. It is not equal to yi because the initial position of the ball is here. The ball starts at the balcony at some height away from the reference point. That means that our initial position is a vector that moves from 0 to here. It is this vector here, yi. It is some height, let's say 10 meters, maybe 5 meters, or 15 meters, whatever the case that it might be, but it's not 0. It's a position that is measured from 0 to that height there. Now, this projectile, when it gets thrown, it will move to some height here, and this height will then be measured from 0 to that point there. And I'm going to call this y1, and you can see that this height is positive because actually is a vector that is above 0. Remember, if this is 0, any vectors that are in this direction will be positive, but any vectors that are below 0 will be negative. So this vector is a vector that is pointing in that direction, the positive direction. The ball will continue to increase its height to go to some height there, and if we measure that vector, we'll measure it from 0 and we'll go to that height there, so that now I have y2, which is also positive because it is above the reference frame. It is above the origin, the reference point, which is in the positive direction. Eventually it will reach the maximum height where we'll measure it from 0 going to that direction. And now here we're going to have y max, which is also positive. And as usual, the ball will then stop momentarily and change direction to come back to these heights that it occupied until it hits the balcony. It will stop where it started at some height away from the reference frame, this height here away from the reference frame. And of course, these heights are also measured from 0. It will come there, it will come here until it gets to the reference frame. Now, how do we draw this graph? This should be an interesting one. So this is question 3.1. To draw this graph, we use the same technique. It's really not difficult. We're going to say y final is given by 1/2 the acceleration due to gravity time squared plus v initial change in t plus y initial. Now here we are going to have 1/2 times negative 9.8 change in t squared plus v initial change in t. Now remember, here we have yi, we have some height here. It could be any height really. If you are given any problem, you will specify it what height it is. Now we can see here that we have our 9.8 to be negative. It will make the whole thing here to be negative, which is a on our standard form of the quadratic equation. When the a is negative, we expect to get a sad graph. But also this graph will start from a height y initial, which is not 0, it's some height above the reference frame here. It's a positive height, in fact. Now this means when I draw my graph here, I'll have my position measured in meters. So I'm going to put the title as well to say y versus time, right? Y for position, because we're looking at position in the y direction. Remember, the projectile moves in the vertical direction. Now here I'm going to have my x-axis, which is actually defined by time, is the independent variable. Now this is 0. This 0 represents when the time is 0, and also it represents when the position is 0, meaning the reference frame. As I said, this is the reference frame in terms of looking at the y-axis, is where the position is 0. Now this object begins by being at some position here, positive y initial. It doesn't start at 0 this time, it starts at some height above 0 here at the balcony. And it's a positive position because it is in the positive direction when we measure it from 0 to here. And we're saying here that we expect a positive graph or happy graph. Now that means our graph will move like that. Notice that I've ended my graph here because this is where it ended. It ends at the reference, it ends at the balcony, not the reference frame. It ends at the balcony. So this is the balcony, then the object comes back to the balcony. I do not pass and go down there, because if I go down there, it means I'm going downwards to the ground, and the ball didn't get to that point. And that's how you simply will draw that graph. As usual, from here to here, it represents upward motion, and from here to here, it represents downward motion. And we can see that it occupies positive height as the time goes on until we get to the maximum height, and we occupy the same heights going down until we get to the balcony where we started. I hope this method makes drawing vertical projectile motion graphs easy, because I do understand that there are many ways of drawing them, but I think this is the easiest method that will never go wrong in an exam if you follow these step-by-step processes. I am going to challenge you again that you do 3.2 on your own and see if you are able to use this method and draw the correct graph. And the answers are on the study guide as well. If you download the study guide, you should be able to compare your answer and the answers that are on the study guide. This leads me to question 4, where we're going to look at a different scenario again, where the ball is thrown vertically upwards from the edge of the balcony and then falls back down. Eventually, it strikes the ground. Take the reference point as the ground. We then say again here, the reference point is the ground. Now, this is the same question as question 2, except we have changed the reference point. Remember, in question 2, the reference point was here. We now saying the reference point is on the ground. Now, I'm giving you these different scenarios because that's how question papers will come. They always change the reference point to be the ground or the balcony or wherever they choose. So I'm just challenging you so that you learn and practice to draw these graphs on different reference points. So we're ignoring air friction as well here, and we say 4.1, draw the position versus time graph for the ball. Take down as negative. Again, the first thing that we're going to do here is that we are going to acknowledge that G is equals to negative 9.8 meters per second squared, because it is actually going down and down is negative. Remember here we are choosing our direction such that up is positive since down is negative here. And as you can see that our initial position yi is actually equal to some height above the reference point. Maybe it can be 10 meters or 15 or whatever, but it is not 0. It is a height here, is a vector that moves from 0 to here. So now if we draw this graph again using these two pieces of information, question 4, we can see that our position versus time graph will actually be drawn such that our y-axis will be represented by the position y measured in meters, and we are going to have the time here measured in seconds. And we're saying here the time is 0 and the position is 0, meaning it is the reference frame as well. Now the object starts at some height here above the reference point, which we said is positive yi, because we said the vector that moves from 0 to there is actually a positive vector. Remember, I'm drawing here my reference frame so that this is positive, this is negative. Now, the vectors that are measured from 0 going upwards, the positions will be positive, but the ones that are going down will be negative. That's why here we have a positive yi, because the ball starts there at yi. Now, yi is our y-intercept, right? This yi here is actually our y-intercept because it is the c on the quadratic formula, our quadratic function. So that's where the graph will intercept the y-axis here. But we are saying that because the 9.8 is negative, it will then make this graph to be a sad graph. And here that's where we're going to start to plot the y. So our graph will then move like this, come back to the balcony, but it will then further go downwards. Okay, so I've drawn an extended line there. It will go downwards and come back to the reference frame. Now, let's interpret this. The graph will move from the reference frame and come back to the reference frame. This is this part of the graph. We start here, not the reference frame, but the balcony. We start here on the balcony. We go up and come down. Remember, from here to here is up, from here to here is down. Then we get to the balcony. Now, after getting to the balcony, we pass through the balcony and go to the ground. The ground is 0, is measured as 0. In other words, here is this height here now represents the ground because that's where we start measuring. So it means this piece from here to there is below the balcony. We are going below the balcony. And our projectile ends up here hitting the ground, which is 0 now, the reference frame. Again, in question 4.2, I'll give you a chance to practice this method by doing the same graph, but when you choose down as positive in this case. We are then now going to look at question 5, which looks at a ball that is being dropped from the edge of the balcony and eventually strikes the ground. Now we say here, assume that the balcony is the reference frame. Now we are saying the balcony is a 0 point, is where we measure our position to be 0. Our position to be 0, and we ignore the effects of air friction. Then 5.1 says, draw the position versus time graph for the ball. Take down as negative. Again, that would mean my direction is sitting such that anything that goes up, the vectors that go up are positive and the vectors that go down are negative. Now, if I extract my reference frame so that I draw the y-axis, you would see that my 0 would be at this point, meaning this is where I start to measure. Any positions that I measure in this direction will be negative because, they're in the negative direction. And any positions that I measure in this direction will actually be positive because they're in the positive direction. But we can see that actually the ball starts its motion here on the balcony, which is the 0 point, the reference frame. So that's why here I'm saying yi, initial position, is the same as the reference point and is the same as 0. because that's where the ball starts. It starts exactly at the reference point. Because this ball is dropped, it will then go down to some position here, and you can see now we are going to measure a vector that goes from 0 to that point. I'm going to call this vector y1. Now this vector will be negative because it goes in the negative direction. The ball will continue falling down and occupies a new position which we measure from 0 to here, and this position will indeed be a negative, not positive, but a negative y2 because it's the next position following that one. Then eventually the last position would be the ball being on the ground. So we measure this from here to that, and we are going to have the final position here. Maybe we can call it YF if we like, because that's where the ball will end its motion by hitting the ground. Now, when we look at this situation, we can see that the acceleration due to gravity will point downward. It always does, and it will be given by 9.8 meters per second squared, and it's going to be negative because it really goes in this negative direction that we chose. It is below, it is going in the direction that is below the reference point as well, you know. Now this means we are going to have a set graph if we remember our equation of the quadratic equation, because this graph really is a quadratic equation. But the other interesting thing that we have to look at is that our I initial is actually 0 meters, right? And this is the y-intercept. Remember, this is the y-intercept. This is where the graph will cut the y-axis. But you have to notice that the motion that we have now is only one part of motion. It is not the same as up and down. That means when we look at our set graph here, we have to restrict this graph. We have to cut this graph here in the middle so that we have two parts to it and we take one part. But you must remember that moving from, let me get a highlighter to explain this one. Moving from here to here is actually going upwards, and moving from the maximum height and coming here is actually going downwards. Now if we look at our projectile is going downwards, that means when we restrict our graph, when we cut our graph here in half, we are going to take this part of the graph and throw away this part. So that means I'm going to erase this part here because it shows when the graph goes upwards. Now I'm only left with the part where the graph goes downwards, which is here, it's going downwards here. So it means I'm going to plot this. Now here is the top, is where the projectile starts. It means here is going to be my 0, it's going to be my y initial. This part will be 0, and all this will be the other heights that it occupies. Now when we look at this question and answer it, is question 5, and we are still drawing position versus time graph. Now here we, as usual, we have our position measured in meters. We also have our time measured in seconds, and we're saying the time here is 0 and the position is 0, the reference frame. Now this is where the graph will start. The graph will start here at 0, where the position is 0 and the time is 0, and it will be a graph that goes down like that. Okay, this thing is giving me a straight line. It will be a graph that goes like that, right? So you can draw a nice curve there. Now when we look at this and try to interpret this, we will see that here, when the time is 0, the position is 0. That's when we are at the reference frame, because that's where we start measuring, is the reference point, where our initial position is 0. As we increase the time to t1, the position also increases. We go to position 1. It gets larger because it moves from 0. It moves from 0 and come to y1, but it is in the negative direction. As we increase the time to t2, we also increase the position so that we are in y2, which is negative. And we increase this again until we get to the ground there, which is, the final position that is negative as well. So we get the expected results. And that's how you'll draw a position versus time graph for an object that is thrown, that is dropped downwards. I'll leave 5.2 for you to attempt and see if you get the correct graph using this method. Remember, all this study guide is attached in the comment section below. Click on the link and download this free copy and use it to practice. Question 6 is the same situation that we did in the previous question, but we changed the reference frame now. We say the ground is the reference frame. Again, I'll leave this to you. I think you see the pattern now. It will be nice for you to practice on your own. The answers are also here on the study guide. I think what I wanted to do to close this section is question 7. I think this one is important for me to explain it because it's a bit different compared to what we've been doing. Now here they say a ball is thrown vertically downwards from the edge of the balcony and it eventually strikes the ground. The balcony is the reference point, right? We're saying here is the reference point, is where we measure our 0. Our y0, the reference point, is equal to 0. That's where we start measuring our position. And there's no air resistance, meaning the projectile is moving in free fall. 7.1 says draw a position versus time graph for the ball. Take down as negative. Now this quickly, already we know it means that vectors that are going downwards are negative. And that would mean vectors that are going up are actually positive. Now, if we draw our reference frame enlarged here, we can see that this will be negative and this will be positive according to this direction that we have chosen, or we are told to choose. But here, that's where we start measuring our position. Now, this position is the position where the ball starts moving. In other words, it is also the initial position. So the reference frame y0 is the same as the initial position, and they are both 0 because that's where the object starts moving. It starts moving where we measure our 0. But here is the thing here that's different. This object starts moving with a velocity v. It is not dropped. It is actually thrown downwards. It is been given some velocity to move downwards. Now, it will definitely come to some position here which will be negative y1, and go to the next position which will be negative y2, and eventually strikes the ground here, which will have our final position, which is also going to be negative. So it's going to occupy positions that are going down and are negative. So here we have the initial position to be 0 meters. We also have g to be negative 9.8 meters per second squared, because really our g is going down, always pointing towards the center of the earth. And we have said here that vectors that go down are negative. That's why I'm saying this is negative. Now, this means here I'm going to have my Z graph given by that curve there, because my g is negative, so it has to be a Z graph. But when we look at this graph, we can see in the same way that we did in the previous question that actually the motion is occurring in the downward part. In other words, we're going to take this part of the graph which represents downwards, and that means we're going to chop this part because it represents upwards. But now here, what is unique, and I want you to listen to this very careful and not make a mistake on this one. Always remember this one. What is unique is that we have the initial velocity. We don't start at 0. If that is the case, we actually going to chop the graph a little bit more so that we start where it's a bit steep. It doesn't have the turning point like that. It's chopped a little bit where it's steep. So we're going to draw our graph from where it's steep. So this means here, that's where we're going to have our y initial to be 0 meters. Now, let's put all this information together into a sketch. If we look at question 7, I'm going to have position versus time graph, and we are going to have our y in meters, which is the position in the y direction, and we are going to then also have our time measured in seconds. Now remember that this graph should be in the negative direction. It should be in the drawn in negative direction because we said it occupies negative positions here. So it's a graph that should be here in the negative direction. But I'm going to draw this graph like this. If you look at my graph here, it doesn't have the turning point. It's not like this. It doesn't have this part here. It's actually steep like that. Maybe if I could redraw it so that it is steep. We chopped that part where it is actually should be like that because we have an initial velocity here, vi. Always do that when we have vi. But when it is 0, when it is dropped, we can draw it nicely as a curve that has a turning point. So you remove the part of the turning point here. I will explain to you why we're doing this when I do a summary of all these graphs, because I need to explain all these graphs before I can explain some of these details. But at this stage, just know that when the velocity is given, when we have the initial velocity to be any number other than 0, we have a steep graph here where it starts. Stay tuned for the next graph, which will be a velocity versus time graph.